Good afternoon, everyone, and welcome to the EOL seminar series. Dr. Jothiram Vivekanandan, or Vivek as he is known by many, will be our first EOL staff member to give a seminar this year. So he gets a gold star for volunteering to share his current research with us on the ever-elusive APAR. Vivek is a senior scientist at EOL. His research interest in all things radar, LiDAR, and microwave radiometer have never wavered since he received his master's at the Indian Institute of Technology in microwave and radar engineering, and later his PhD in electrical engineering at Colorado State University. Vivek is a fellow of the American Meteorological Society and serves as an associate editor for Radio Science. He is a recipient of the 2018 Christian Huygens, I think I pronounced that correctly, Huygens Medal for his work on cloud microphysics. He was part of the development team that added a multimeter wave radar to NCAR's S-pole and was instrumental in developing the NSF-funded cloud radar for the G5. Pertinent to this seminar, Vivek led the writing team that wrote the current APAR proposal. In his words, APAR is a transformative technology for weather remote sensing with several novel ideas and concepts. At EOL, questions abound about what's happening with APAR. What I'd like to know is, what is APAR? Vivek will be introducing APAR, among other things, in his seminar today. For those of you who are watching online, please type your questions at the Slido window, which is located at the bottom of the presentation screen. We're going to save those and read those out at the end of Vivek's seminar. Dr. Vivekanandan, the stage is yours.
Thank you all. Good afternoon. Thank you, Jackie, for the kind introduction. At the outset, I'd like to share with you what's a digital twin. Digital twin is a virtual representation of an object. I mean, you have done a lot of simulations. Most of you do a lot of simulations about a system or a model. In an object, as in this case a radar, the radar has many subsystems, like it has a transmitter, receiver, waveform generator, amplifier, and all those things. And the characterization of all those things. Plus, it's a characteristics, like for example, spatial, temporal resolution of a radar, sensitivity. All these characteristics, how do you understand those things so that you can come up with a best optimal system? That's what digital twin does it. It's a rich environment where we can look at subsystem interfaces, then decide which is the best one data rate-wise. What's the best sensitivity you can get out of that? And that's what digital twin does. Digital twin is basically a virtual representation of an object, in this case, the radar. I'd like to thank my co-authors. Adam Krabowski is in the audience here, Eric Lau, Christopher Berhardt, and Eric Turing. I also like to thank APAR team preparing proposals and budgets for NSF and the NCAR, say NSF and NOAA, supporting day-to-day APAR activities. Without them, we wouldn't have come this far into this presentation here. This talk today consists of three main sections. The first part, I'll introduce phase array radar, which is common for both ground or airborne. It doesn't matter which one it is, phase array radar. The second part will deal with specifically to the APAR radar. Then third part will be digital twin. So that the first two parts, introduction of phase array radar and APAR, will help to understand the last part, digital twin, much easier than otherwise. Okay, that's how I'm going to take this presentation today. In the community, there are many phase radars designed for sensing atmosphere. The top left shows a rapid DAO. That was like a 2001, this is more than 20 years ago. NCAR was involved in designing a frequency. In this case, it's a X-band, about 10 gigahertz, where the frequency is scanned, give the delay, so that we could get the scans every 10 seconds, much faster compared to minutes. It's called rapid DAO. It's turned in mechanically in azimuthal mode, but in elevation, it goes with the frequency scanning. This is a phased array system. It's a waveguide, many elements in this one. Verman and Randall, and they have paper on that one. Then ISF, Steve Cohn, they had a mapper about 900 megahertz. This is the 4 beams, the 4 panels, where we got a fat beam illuminates the big volume, then 4 different fixed phase shifts, cross-correlates the signal, get the 3D win. What's the advantage? In these 2 systems, for example, if you've got a 3D wind profiler, it's usually done by mechanically scanning DBS, digital beam swinging system. It takes 30 minutes to get a wind profiler, but the mapper can do in less than 5 minutes. That's how it's been done. So they're much faster. Same thing with the upper system, the X-band system. In 10 seconds compared to minutes, can do scans like that. These are the examples of phased array systems which EOL had interactions and developed quite a bit. On the top right is a NWRT, NSSL. They have the phased array radar system. They are pioneered in this one long time. In the top 2 panels, you see the cross sections of a thunderstorm. They are done about 5 minutes apart. All the bottom ones are done every 30 seconds using the phased array system. That means the representation between 5 minutes versus 30 seconds, that's much different and much faster system where you can get those systems like that. Hence, the evolving system could be represented much better in a temporal scale, also in spatial scale. University of Oklahoma in Norman, they got a MRI funding in about 5 years ago to develop the bottommost system here is a C-band phased array radar system. This system basically is the same frequency as what we plan to do on a C130 APAR C-band, but 5 gigahertz. It has 1.5 degree beam. It's a much bigger aperture ground-based system. Also, it can do a fan beam and a pencil beam. Like that means it can image very fast. Airborne. This is atmospheric imaging polarimetric radar. It's a pair. Polarimetric imaging atmospheric radar. So this system is operational now. It's been funded, they've been developed it, it's working now. This is the closest system in a ground-based configuration what we plan to develop in NCAR. That's a pair system. Okay, before we get there, NCAR always has a big thing about scientific motivation. Why do you want to do that? What is the purpose of this whole system? We have SPOL, we have other radars here, HCR, so many other remote sensors. What is special about APAR? In microphysics is poorly understood, linking dynamics and thermodynamics. Microphysics, in this case, what we mean is in a cloud, say ice versus liquid. How big the ice particles? Does it have a hail? Does it have a raindrops or cloud drops, a cloud ice? These things has to be understood well so that the link between dynamics and thermodynamics could be well understood. If you can do that, you can do a much better, precise forecast of weather. And also, we can have a less uncertainty in climate models. And that's the whole scientific driver why you want to do this. Now, the question comes, why on an airborne platform? Why not a ground-based radar? Like people have done ground-based radars. A little bit easier compared to airborne platform. It's much more complicated. Why you want to do that? If you want to measure wind, not radial wind. SPOL can do radial winds. Along the beam, it can measure the wind. It can't measure 3D winds. It can't do it. To do that, we need 2 radars separated from baseline, say about 30 kilometers, 20 kilometers apart. Then look at some angle, 2 beams. Then called dual-Doppler. With that, we could able to get a 3D winds. But APAR, or Airborne Phaser Radar, will be on a moving platform. In that way, as the platform moves, you can get dual-Doppler winds. This is the only platform can do dual-Doppler winds. With micro patch antennas, it can do polarimetric measurements. Getting the microphysics, difference between ice and liquid, and also 3D winds, it's possible only by the one platform, APAR. Otherwise, you have multiple systems you need to have it. More than 2 radars, you should have it minimum to get the wind measurement. It's not necessary. That's the main instrumentation advantage with the APAR. Having that one platform, we can do 3D winds, plus we can also do cloud versus liquid identification can be done. The other part is many of these like tropical cyclones, they originate far in oceans, remote places. They're not close to land surface where your radar can look at it. In those cases, and also many of the storms, orographic, like a mountainous terrain based, can't be observed easily by a radar on the ground because a lot of clutter and everything involved in that one. In those cases, Airborne platform is the ideal candidate to do that kind of work. Go far into the ocean, go above the mountain, get some measurements like that. Also, a storm evolves, it's not going to be stationary. It follows, it kind of moves really fast, like a tornadoes and squall line. The APAR can follow and get the measurements from genesis to intensification and dissipation. And these are the finer aspects of Airborne platform where we could use this system unique. No one has done this system in the community. No one has any of the system like this. It's the first weather airborne radar on a C-130. Let me give a brief introduction to phase radar concepts here. The PAR antenna consists of an array of elements. It could be 8, it could be 100, it could be thousands. Then like a S-pole has just one transmitter, klystron. That's it. It can transmit the megawatts of power. But in this case, we have a small elements. These are solid state, either gallium arsenide or gallium nitride amplifiers. These are about maximum power, about 10 watts, 15 watts. That's all it can give it to us, not more than that. It's an array of elements. The radiation from that gets basically interferes and forms the beam. In the figure A, it shows that each array as a, let me get a pointer here. That way I can point it easier. Okay. Each array has a phase shifter. See, this is a radiating element here. Each one of the phase shifter. If you want to steer the beam electronically, there is no moving parts here. Electronic scanning. Electronic scanning, basically, it's a phase shift. It's a time delay. That's all to it. If you want to scan, say, 61 degrees from the bore side, then the phase shift about 20 degrees you have to give it. Each on 20, 40, 60, 80, like that. That's what you give it. Like you say that pi, 2 pi, 3 pi, 4 pi, like that. If you want to scan 30 degrees from the bore side, 90 degrees, then steering, it should be a 30-degree phase shift has to be given like that. Is that right? 90-degree phase shift will give you 30-degree beam shift. NCAR phase shifts are given to steer the beam from one angle to other angle. And 61 degrees needed for 20-degree steering the beam, 9 degrees for 30 degree. This is antennas spaced at lambda by 2 distance. The lambda and the C band is about 5 centimeter. Talking about 2.5 centimeter apart, elements are placed in aperture. The other issue here is the figure B shows the pattern of radiation pattern. When you scan away from the bore side like that, beam becomes fatter. It is not same. The beam width changes because the aperture, which is on the bore side, it's perpendicular to it. When you go away from the aperture, the apparent aperture, what you look at is smaller than actual aperture. Because of that, the beam becomes wider. And the beam width and the gain changes in the phase rate. That's a complication what we have to face. But this could be corrected. It's an engineering problem. It's well known. Give a simple example here. In this case, we have 8 linear array elements. These are about 8 elements here. at spacing about 2.7 centimeter or 27 millimeter here. This is lambda by 2 spacing. With this system, how does it look like that? What's the beam width? The beam width is proportional to how long the array is in this case. The longer the array, like for example, the beam width proportional to the depth, the distance or diameter of the aperture. The bigger the aperture, smaller the beam. Proportional to lambda also. That's how it applies to whether it's a S-pole or any radar, the same concept, doesn't matter. Now, if you have n is number of elements here, you have 8 elements, the beam width will be about 13 degrees, 100 by 8, roughly about 13 degrees or so. That's the beam width of that system, as simple as that. If you have an array of n by n, is that right? Then you look at a pencil beam. Again, it's 13 degrees in that case. For example, the SAP, what we call in phaser radar, it will be a building block, 8 by 8 element that will have that big a wide beam width. That's what will have it. The overall beam width is element beam width times the array geometry, so that you get a very pointed pencil beams. Now, this is the beam of a linear array. In the top portion shows without steering here. As soon as you steer it about, say, 30 degrees, giving 90-degree phase shift, then beam becomes broader. Then also notice that the side lobes, this is the main beam here, the side lobes are only 13 dB lower than a main lobe. That is not good. We need to have at least about 25 or 35 dB side lobe to get a good measurement. It's not good. And so what we do in a phaser radar system is we weight the elements. We don't transmit uniformly all the elements. We weight them. Like this is the distance on the linear scale, how it distributed. The power is lower on the end systems, higher in the center system. If you weight the system like this, the beam width will look like this. So if you uniform, where all the elements are same power, the blue color, see it has about 13 dB side lobe, minus 13 side lobe like that. But if you weight in the Taylor, in this case, some kind of weighting, like I showed you in this one, a Taylor window, then the red color here shows side lobe much lower, except beam width is a little bit broader here, but side lobes are lower. And these are the things of beam characteristics. In a phaser radar system, the gain changes away from the bore side. Then again, if you want to get lower side lobe, you got to weight the aperture. And that means we're not transmitting a full power because we're weighting less power in the end elements. That's then other problem like that. Then the next constant phaser radar is agility. Beam agility is the key of the APAR system. In a traditional radar like S-pole or NCAR, it takes seconds to scan to one place to other. But here, it takes microseconds. That means it's instantly we can scan one place to other. How does it help? Instantly scanning, right? One place to other, we can change without no mechanical movement. If the phase shifts are given, so you can scan from one angle, theta and phi here, you can go to different elevation azimuth like that. And that could be done in one phase radar system, having that phase shifts. Why does it make a difference? If you look at this system here, in a traditional reflector radar, what gives you like the coarse measurement in a temporal scale. Many things are missing here. In a phase radar system, because of beam agility, we got a rich presentation, almost continuous. We don't have missing things like that. We got a contiguous measurement like that. And that's the difference. The beam agility, where it gives you a lot more, much faster, much finer resolution could be done. But that all comes with the price. I'll come to that later. It's not something is, straightforward, but there is a thing. But engineering challenges, it's a very good challenge to have it to make it better. Also, given that how we can control the beam with the phase shift antenna, we can shape the beam on the fly. It could be broad beam, or a pencil beam, or a fan beam. So all could be done. We don't have to design a horn so that gives only 1 degree beam all the time the same way. We can do it much differently. And these are the things what we can achieve. We can do that. How we can do faster scanning electronically, but anything with the atmospheric sensing, we are talking about a lot of these small targets, either raindrops, ice particles, billions of particles in a kilometer scale volume like that. They're all moving to each other, right? Hence, the signal what we get is highly fluctuating. What we get in a received signal is highly fluctuating. We need to average them out. Otherwise, it will be very noisy looking signal. And we can average them out. In say a 2000 PRF, in this case, for example, here, that means every half a microsecond, basically, you're transmitting a pulse half a microsecond. But these targets realign, shuffle itself. Typically, depending upon the spectrum width they call it, that's a Doppler spectrum, how the particle relative to move to each other. They take typically about 5 milliseconds. That means you are staring a resolution volume for long, for getting no gain out of it, because the samples what we get is not independent. Because independent samples, you can reduce the fluctuations. The dependent sample is not going to help you out. Phase radar system can move the beam one place to other, such a fast mode, independent samples. That way, we can scan the volume much faster with a less number of samples. I will explain a bit more into this. This is a radar pulse, returned echo. We have on the y-axis is a correlation coefficient. X-axis is the time between the samples in milliseconds. See, the signal is highly correlated, zero lag. See, the red line corresponds to bigger spectral width. That means particles are fluctuating much faster in the resolution volume. Then if you want to go for highly uncorrelated samples, it takes about 5 milliseconds. Till 5 milliseconds, samples are correlated. Hence, not much use. We want to get independent samples. Within that half a microsecond PRT, that 5 millisecond, we have so much time, then we could scan a different place, come back after 5 milliseconds, get the same looking independent sample. That's how phase array does it. Let me show you with the cartoon here. And the top, what you see here, is the contiguous pulse, like a S-pole. It transmits the same location, same thing like that. Keep on the same pulses like that. But in phase array, it's going to be multiplexing. This is a beam position 1, say theta and a phi, elevation azimuth. Beam position 2, theta 2 and phi azimuth, different elevation scan. What it will do is, it will scan 2 pulses, go to the next one, some other beam location, can go to the measurement, then third one, and the fourth one, then come back here like that. It's called beam multiplexing. That's how you can get independent samples if you desire to do so. Okay, how does it help independent samples? This example shows signal to noise ratio on the x-axis here, then standard deviation, the fluctuation, the measurement. The red line shows the IPS, independent sampling using a phase radar system. If you look at this one, see, even the 20 samples, sample pairs, you can get a much lower fluctuation in the measurement signal compared to 120 samples like in the S-pole. Still, you aren't getting the same thing. In phase radar system, with a less number of samples, because independent, you can get a much better accuracy. This is only for power measurement. If you come to velocity measurement, Doppler measurement, that's different. The velocity measurement is other way around. We need a correlated samples, velocity measurements, Doppler measurements. Hence, the red, which is IPS, independent sampling, it doesn't help you. You need to go for much higher signal to noise ratio. For just a DBZ measurement, like a surveillance, power measurement, it's good. Hence, there are always challenges when you do this one, how to make use of the scanning of phase radar system. There are optimal scanning. For a velocity, you got a correlated samples. For a power, independent samples are okay. And these are the main things. For example, here it shows a scanning strategy. In this case, what I'm showing is elevation scan with the 2000 PRF. We can do that in the case of, if you look at the notes below here, there are 18 groups here in this one. Each group has about six different scan positions, 5 and 35. There are 2 beams, basically getting a dual Doppler measurements in this case, right? In each group, it's getting down to 5 milliseconds. You can do each group, the 20 times. That means basically the amount of time the phase radar takes about 1.8 seconds compared to a radar which does continuous scanning, like S-pole. It can do about 5 seconds. That means that 3 times phase radar is much faster. Get the same number of samples or to get the same kind of measurements at a much lower standard deviation. And so this is a one scan strategy how phase radar system works. These are 2 things I described. One is the beam characteristics, beam agility, how fast it does. The third part is the pulse compression. I mentioned in the beginning, these elements, very low power devices, 8 to 10 watts or 20 watts, the maximum you can get. These are solid state amplifiers. With that, even your 2,000 of them, you have it. APAR is 2,000 of them. Even then, you got a 40 kilowatt. It's like a megawatt. Then how do you get good sensitivity? We need a more power. And for that, we use the pulse compression. The pulse compression is, in the traditional radar, in the case of a S-pole, you got a 1 megahertz, basically 1 microsecond pulse with 1 megahertz bandwidth, 150 meter resolution, get measurements. In phase radar system, the pulse is modulated, FM modulated. That means it has more frequencies packed into it. Now, in the top part here is the 5 megahertz bandwidth with a 40 microsecond long pulse. This is compared to 1 microsecond, 40 microsecond. 40 microsecond pulse has 6 kilometer range resolution. That means we can't resolve objects less than away from 6 kilometers away, each between them, then we can resolve them. Otherwise, we can't do it. But the pulse compression, where we have a lot more signals, frequency packed, then we can compress the signal like that. The bottom shows compressed pulse. That way, we can resolve even 30 meter because we have 5 megahertz 5 megahertz bandwidth with a 40 microsecond pulse. And the top right panel shows uncompressed pulse. You don't see anything in there. The bottom panel shows how we resolve the 2 objects. They are within the pulse width in 6 kilometers. You can resolve it. That's the pulse compression. And transmitting a long pulse, more energy. In this case, 40 microsecond pulse compressed to say 1 microsecond. The 16 dB gain, theoretically, you can get out of this one. That means we can bump up the sensitivity more than 10 dB using a pulse compression. These are the 3 main components of phase radar system: the beam, agility, pulse compression. These all the things has to be understood quite well. That's why digital twin plays a critical role in this, how we define a phase radar systems. Now, let me come to a cartoon here. What we have done in NCAR, Eldora radar, it's basically airborne Doppler radar. We have done this in a hurricane measurements, 3D winds, using this radar system. Done many years. And so this is like basically, there's no polarization in this. It does basically does a wind measurement, the dual Doppler. But the slotted waveguides, 2 beams separated by 35 degrees, it takes a measurement, gets a dual Doppler winds measurement. Then S-pole radar here. The polarimetric radar, the polarization, it can give us liquid versus ice separation. We know that. We have done that very well. Now, the APAR combines both of them together. Basically, a dual Doppler with a polarization concept because microwave patch antennas, we can do that. It can combine both winds, 3D winds, with liquid or ice discrimination. That is the key aspect of this thing. Now, let me see whether I can do this. Yeah. This animation on a C-130, how the radar look like. It has 4 panels, 2 on each side of the fuselage. Each is a 2-meter size, 2-degree beam width, 5 gigahertz, one on the top, one on the bottom. The 4 of them, they're identical, so that we can interchange them if necessary like that. And this system is called ASA, Active Electronic Scanning Array. It has more than 2,000 radiating elements in this one. How does it scan? I'm sorry. Okay. Given that how the radar is located here like that, we have three types of scans. Surveillance scan. Let me go back the pointer here, 1 second. Here a surveillance scan, which is shown in this color, gray color here. Dual-Doppler scans, dual-pole, this is for microphysical measurement. Doppler, microphysical measurement, surveillance. It's a unique feature of the system. It can do surveillance. Eldora can't do surveillance with the previous airborne Doppler radar. This can do surveillance scan, including all this nose cone radar and the side radars and back and the radar and the cargo door like that. Then you can swing the beam so that you get the wind measurement. Then also it can do polarimetric measurement. Now, in technical advance, when you summarize it so far, what I said is adaptable to, we can build it like a tile by tile. For example, here, got one element here. This is only about less than 3 centimeter big. This is one element. Then we can make it like a 8 by 8, called a SAP, single array panel, 8 by 8. Then you can put all the 8 by 8 combined with 37 of them in this case, make it electronic scanning array, about 2-degree beam width. If you want to make it 1-degree beam width, you need a much bigger area you need it. And C130, the available aperture for is about 2 meters are good. That's what 2-degree beam widths are selected. Why with the C-band? The C-band is a lesser attenuation compared to X-band. X-band is 10 gigahertz. Now, if you look at this picture here, this is taken by X-band radar. The radar is basically Eldora track is shown here. Shows the rain bands here. You don't see much with that. But look at it, how strong is it when the Eldora goes closer to the rain band. Because of attenuation, it doesn't see the inner rain bands. But with if you go to closer, you can see that one. The C-band, compared to X-band, that's a 10 versus 5 gigahertz, the absorption in the precipitation will be about 3 to 4 times lower because of it can do deeper into the cloud. And the C-band is much more preferable for that case. The engineering advancements, if you look at it, then it's a fault-tolerant system. It has many radiators. It's not just one klystron. If it fails, it fails. But we have even about 20% failed elements in this one. Still, it will perform satisfactorily in the field. That's how it will be designed like that. And so this system has agility in the beam, adaptive scanning. That means we could scan as you wanted. You don't have to go sequentially to scan something like that. You can go one area, go to a different area. You're not interested in this stratiform case. You want in a convective case, you can go back quickly. Other place, adaptive scanning is possible. The imaging is we can create a fan beam, like in this case. A 20-degree fan beam could be created, then come up with the pencil beams. That means as if with a photograph, we can take the measurements such a fast mode, like a tornadoes. We need that every 10 seconds, second measurement, we can do with this. And these are the finer features of phased radar systems, where beam agility, the beam shaping, all these things could be done in a software. It's not well defined before hardware like that. The hardware is defined, but in software, we can change many of these aspects so that we can make the system work as we need it. Here I show the block diagram. A simple radar block diagram is, if you look at it in S-pole, is much more easier. This is similar to this, except we grouped into 3 different categories. What you see is the blue color is called the front end. That is all of this front end, that is antenna, TR modules, power distribution, digital receiver, exciters, all of them are located outside of the fuselage. The green box is a backend. It's what resides inside the fuselage. That basically radar scanner processor software displays. Then other color aircraft specific, there's a C-130, the power and GPS signals is the third one. So the blue part, the front end part, UIL come up with a preliminary design. We talked to the aerospace companies. They will build that front end part for us. Then we could test them and get them. The green part, which is a backend, radar backend, we are experts. We have done that many years, many radar systems. But this is a bit complicated, but could be done. And that's our response. We can do that. You have to put it together. Look, the aerospace company designed this front end. We are doing a back end. It has to talk to each other. That's why digital twin is so important, so that could we understand the system end to end, so that the system functions as we expect it to do it. Architecture-wise, it's important to understand. Phase radar has a different architecture. We can offer many types of architecture. What I show here is the analog architecture here. Each of the radiating element, this is like a one power amplifier. It has basically a power amplifier here, the LNA, low noise amplifier here. Each has a phase shifter like that. Then this is the simplest configuration where you have each one as a one phase shifter, then one power amplifier like that. It's called analog beamformer. There's no digital in this case. The phase shifter like that. Now, the other extreme is digital. The right side shows the digital configuration where we don't have a phase shifter. See, like this, we don't have phase shifters here. It has just transmit amplifier, receive amplifier, that's all it has. Everything is done digitally. The phase shift is basically a complex multiplication of the signal, and that done digitally could be done. But problem with that is we need too many digital to analog converter, analog digital converter. That is not affordable at some point. Hence, there is a mid path. We don't want to go fully digital, which is not possible. We can't go to fully analog, which is kind of set in the zone sometimes. We don't have that flexibility. We took a mid approach called hybrid beamformer, or hybrid architecture in this case. It has analog and digital. If you want to do, in this case, what happens is each of the element will have a phase shifter, but they are formed as sub-arrays. We have 56 sub-arrays out of 2,000 elements. We have it in that. These sub-arrays, it could be used each as a basically a phase shift. We can scan azimuthally using analog phase shifter. We can do an elevation digital. Hence, it can do digital beamformer here, analog beamformer here like that. It's a combination of both. Hence, we have chosen the best what we could do, like a hybrid, where we can do both analog or digital. And this system, the reason what we did is, if we want to fully analog, we can do that also. Or fully digital, we cannot do it, but we can have analog and digital, we can do it like that. And this system has that versatility. If you look at how they look like specific to APAR system, this analog architecture here, these are each radiating element here. Then we have the phase shifters and TR switches here. The one digital to analog converter, analog digital converter, that's all to it. In our system, what we have is, we have both hybrid. It has basically, if you look at it, the 37 panels, we have it here in this case, 37 panels. Each panel has 8 by 8. There's 7 of them. There are 56 rows, right? And they're all basically output, they're all combined along this way and horizontally come out of this one. That means we can have just about 7 or 8 DACs like that. Then we can get jobs done. We don't need 2,000 of them like that. Okay, each of them can handle 8 of them, each FPGA, or in this case, RF SOC. Go do that. The architecture, what we have is the hybrid architecture. Now, the data rates, always wonder, so many elements are there. What's the data rate in a phase radar system? The S-pole, we are talking about I and Q. I and Q is the return signal, right? You transmit a pulse, receive signal at a S band or a C band is all I and Q, the impatient quadrature signals here. Then in the case of S-pole, there are 1,000 PRF, typically we use it, 1,000 gates. I and Q are 2. Each one have 16 bits. The 2 channels go on a cross-pole channel. 64 megabits per second in a S-pole radar system. The HCR, Hyper Cloud Radar, this is a W-band system. It has a much higher PRF, 10,000 PRF. It has, again, about 780 gates or so. Then about 500 megabits per second. These are the data rates, what we currently do that. The APAR, the 56 subarrays, it gives you about 63 gigabits per second. It's large. But once you process that, data processing is done, the pulse compression, everything is done, then it becomes about 640 megabits per second is comparable. This is about 100 times, or in fact, 1,000 times bigger than S-pole, but this is about 10 times bigger than S-pole radar system. But there are limitations how much we can data rates, and this is what typically what we plan to do it. A lot of data flows through it. We have subarrays, we can combine them so that we don't have to sample every element in 2,000 of them. We can sample a subarrays like that. We can do that way. We can reduce the data rates. Okay, this is my last part of the presentation here. You understood the first part where the basics, APAR radar systems. Now the digital twin, much easier to follow now. Digital twin, it replicates the front end of this whole radar, radiating elements, the power amplifier, attenuators, and array controller, all the things replicates it. With that alone, we tested, but we need a radar backend also. Then this radar backend takes the radar signal, produces the radar observations. Combining those makes it almost end-to-end system here, so you can validate what we do it. And this is used to evaluate digital data acquisition, control interface, many interfaces we have in the phase radar system, because it, like I showed in the block diagram, it has transmitter, receiver, array controller, waveform generator, so many things, data rate, all those things. It has to interface properly, otherwise we'll have a huge problem with that. It's validate that this digital twin was developed. Now, there is a specialty. Many people have a digital twin. It's not only us, OU, NSSL, University have digital twin, but we have a unique in this one. Usually, in a radar system, it has a beam width, a 1 degree beam width. Then we can scan it and get the measurement, but that's not done like that here. It is done, each element, 2,000, each of them has radiation pattern. That kind of summed over so that it represents the two true characteristics of the phase radar system. It's not, we're assuming a beam is assumed like that. There's no baked-in beam in that one. We do analog beamforming along each row, on the per row, like in an elevation scan like that. To understand that part, you have to understand radar signal flow. See, the blue part is the front-end part, which is done in ASA simulator. The green is what we in the radar backend, where this I and Q, where it comes out here, this is a fully, this type of 5 gigahertz carrier comes up with 63 gigabits per second. This getting processed by radar signal processor for the I and Q here, gets the DBZ, Polarimetric, all the things getting done, that backend, and displays, all the things getting done. Now, if you expand that box here, this box, if you expand that box here, how it is done. The 63 gigabits, each 56 channels, and 56 times 1.1, about 50 gigabits. That much data flows into it from the front end. Then they're all multiplexed into 56 channels here. Then they're basically in beamforming. Remember I talked about digital beamforming elevation plan. That's getting done here. Then demodulate, take out the carrier frequency, get the baseband. Then get the pulse compression to get a better resolution. Then it get processed. And that's how it's done. All these things are part of the RB, the green part. Radar backend is called. Now, how it's done in a diagram here, it shows how the ASA is done. in this algorithm here, the U and V is a Cartesian coordinates. Basically, it's a direction cosines. Like a theta and a phi, azimuth and elevation could map into U and V. U and V is basically a projection of elevation azimuth angle. That's all to it. It gives a uniform sampling in the angular coordinate. That's all to it. Don't worry about U and V. It is like azimuth and elevation. These are those so many points we have in the atmosphere. These are M and N represents the 2,000 elements we have. From there, how do we sample one angle? Getting done by the U and V's are angles here where we're scanning that, then get that transmit response, element gain, the phase shift, given that to steer to the beam like that. Once we do that one, receive the receive pattern, transmit pattern. The next one shows the receive. All those elements back to the one of the elements comes back here. Then this is the radar resolution volume, which has rain or ice or something like that. All the backscatter characteristics multiplied with the transmit characteristics, radar constant, which is the receive power or receive signal, which is a complex in amplitude and the phase. And so that's how the simulator does it. Then to do this part, show in a flow chart, given that how many elements we have 2,000 elements. We have 1,000 range gates. We have 100 elevation angles, 100 azimuth angles. We're talking about 10 million pixels. We got to handle that. It is not easy to do in a real time, but could be done if you pre-compute few things. In this case, we know exactly for the given phase, we know how to steer the beam. And they're pre-computed. That's all done already, so that we don't have to redo some of the computation. That way, this whole digital twin could be run in real time, same as phase radar. It's not like slower than what we look at it. Same as phase radar could be done. It's a similar to block diagram. These are pre-computed here. See, these are the pre-computed components. Like here, we have a cloud resolving model. That simulates a cloud a priori. It's a squall line, a tropical cyclone. It simulates that. It computes all the radar movements. We have that model called basically a CR sim from Sunny, basically State University of New York. We have that code here. We are using that code. The case of AOS. AOS is a APAR observing simulator. It simulates the radar observations. They're all stored already. Then all the pre-computed beamforming question all be done like that. For a given angle, we can select where do you want to scan, then generates, basically it generates loads the movements, get the INQ. INQ is the actual pulse to pulse. How do you get for a given radar movements, you can get INQ. INQ is the in-phase quadrature components. Then that gets propagated through it. Then we have, remember I told you about long pulse and short pulse. Long pulse, 40 microsecond long pulse, because it gives a blind zone. Because 6 kilometers you can't see much in the beginning. And so you have short pulses, 1 microsecond pulse. Both are interleaved. And so they are frequency multiplexed, and they apply the frequency, then combine them, create actual radar return from the atmosphere. That goes in the radar backend. I showed in the green boxes. That's getting done. In the lab, what we have, all the things what is described is how a digital twin, we designed it. The team of APAR team designed that. Now, in the lab, what we have upstairs across my room, this is what the whole ASA is. Like we have a ASA simulator here, the CPU, then general processing units, then FPGAs. With that, this is the basically ASA simulator here. Then a radar backend consists CPU and FPGAs with that. Then this can simulate 10 million weather pixels in real time. You can look at it as if the radar can. Basically, what ASA can say it, we can say it in this one. Radar backend 56 beamforming, the pulse compression, multi-beams. How do you validate this? Okay, we designed the system from the radar transmit and reception. How do you validate that? These are some of the examples of validation here. This is the left side shows the truth, where we have what sampled by the simulator. The right side is what we simulated, and both looks almost identical, the dBz. This is the height and the range. You see how identical are they? They are same almost. That means it's able to replicate what we sampled from the atmosphere to what we're able to look at in a simulation. That means we have confidence the system does work end to end. That's a power measurement. This is a velocity measurement. The left panel shows the velocity here. This is the velocity scale here. The right panel shows the simulated. Both almost same. There's not big a difference here. Hence, we're able to validate the digital twin with the truth, what we know, what we inputted, what we showed. This is a polarimetric measurement here, the ZDR, which is like a horizontal vertical polarization. This is a ZDR measurement. A bit grainy here. See the grainy feature is not as smooth as what we saw. Remember I told you the phase radar system is good for independent sampling. There are times for a ZDR, for a Doppler, you need a correlated samples, we need that. And it's not done properly. That's why it's a grainy feature, what you see here, the height, thing like that. This all can be manipulated later. The bottom line, the APAR system, basically the digital twin of the ASA system, able to replicate what it's supposed to simulate. This is my last slide, summary slide here. The APAR is able to do the concurrent at the same time, because no other system can do this. Concurrently can measure the winds, 3D winds, not just Doppler winds, and microphysics. Why it is important? Diabatically driven. That means the microphysics, how it modulates the storm thermodynamics. To understand that part, we need to have those kind of measurements. If you have that part, you get a better forecast. Also, you can reduce uncertainty in the climate models. APAR represents generational leap. In this case, we are talking about a system highly software dependent, where you can change characteristics depending upon the PI's need or scientific needs, like that could be done. Adapts the phase radar technology. The PAR, because agile beam, adaptive scanning, and pulse compression, we could achieve what we need to do it, but a lot of engineering challenges in this one to do it right. And the digital twin radar backend I showed you, it can show, the validates the whole system end to end. And I would stop at this point if you have any questions. And this is a very exciting project, what UIL has taken up. And the whole APAR team, I mean, the people in the office, not just a scientific, technical part what I described here, the whole APAR team, which we're thankful, because they prepare the budgets and submitting various NOAA, NSF agencies, getting resources to us to make this program move forward. And it's a huge team effort. It's the engineers and the management and upper leadership. And so I'm thankful to all of them and the APAR team. Thank you.
Great, thank you, Vivek. I've been wanting to have someone give an introductory talk on APAR, so thank you very much for stepping up. We have time for questions. Does anyone in the audience or someone on Slido have a question? It seems like someone has a question from Slido.
Mm-hmm. Could you please read me?
Yes, this person, Jay Wilson, asks, excuse me, John, I know my vision's not as good as it used to be. What is the closest range that expect good data, and what would be the minimum sensitivity at that range?
Yeah, good question. APAR transmits both long and short pulses. That way you don't have blind range. Closest what you can see is less than about 1 kilometer or so, depending upon how fast you can switch the system. So we can do that with a 150-meter resolution. The sensitivity is at a 10 kilometer, it's a minus 10 dBz sensitivity. It's at minus 10 dBz is a very light drizzle, that kind of sensitivity it has. And so if you look at it, APAR system, it can look at small cloud features. At the same time, it's a very sensitive radar because you have pulse compression, long pulses and short pulses.
Thank you for that question.
Mm-hmm.
Does anybody from the audience have a question in person? No. What type of maintenance is involved in the upkeep of this instrument? Or what kind of calibration? Are there parts of the instrumentation that would require continuous maintenance and calibration?
Yeah, this is a kind of a novel system. We haven't done much of maintenance with that. Of course, we have plans how to do it right. We'll acquire a chamber where basically it's a chamber, anechoic chamber it's called, where you can put these panels. We can measure the characteristics. Within that panel, the radio frequency measurement could be done, like a beam width, the gain, the characteristic, all could be done. That chamber is about, it will be housed somewhere in the building one here. There's a budget for that. That will be big enough, like it's be at least what, Jonathan, how big is that chamber? Is that
20 feet by 16 feet.
Yeah. Yeah. That big a chamber. This is like what it costs about 400 to 500, 600K, I guess. I don't know how much it costs you that. It's a lot of around that. You know, it's a good one, the expensive one, but at the same time we need that so that it can characterize, because we're talking about a lot of elements here. How it radiate, what kind of attenuation it has, what kind of performance it has, beam width it has. And so we got to characterize them periodically. And so we have those some of the calibration chambers. That's a in-chamber calibration. There are other calibration we can do in the lab electronically. We can measure many other electrical characteristics with that. Then also we'll have like a S-pole radar in the Marshall. We can co-locate with that, take the measurement, simultaneously cross-calibrate. Plus, like a OU I showed. OU as a radar, which is a C-band, similar radar, we can compare with them like that. And so there are other ways also end-to-end could be done. In addition to what we do in engineering-wise, what we can do here, we can do other systems calibration also could be done. I mean, NCAR is well known for the best data quality what you can offer come to any other instrument in the community. That is what makes it UIL stand out. So with that in mind, we planned a lot of calibration system, calibration of various ways how we can do that. And so we'll know as we go along. But what I presented today is just saying that as if it's a regular radar system. Actually, it is not. You have to think out of the box. If you do that, then we can have many more innovation could be done. That's why it's called transformative technology. It is not like a S-pole. It's not like a HCR. It's a totally novel system. The building blocks are done from element to a small sub-panel to a bigger panel like that. This kind of architecture, what we can do, only the phase radar system can do it. Why it is not done so far? Because the cost has been a big factor in this. 10 years ago, the system would have cost 10 times more than what we are costing it today. Because of all the 5G, the system component become much cheaper compared to even about 3 years ago, what we said it. Today is much cheaper. And these are affordable now. Computers have become much faster. Again, the elements, mentioned about radiating elements at about 3 watts, 4 watts, they can turn. Now we can 20 watts could be done. And so these are the innovation. It's been done. People have demonstrated that one. And because of that, we can achieve this radar within our range. But still, we are long ways. We haven't designed system yet. When we are design system, we are still a long ways to go to show it. Yeah.
We have a question from the physical audience.
So I know you said that the large panels, so there's 4 on the plane, they're made identical, right? So that they can be swapped if there were failures. Is the plan to have them be the whole panel able to be switched, or the individual like 8x8 panels could be swapped within the large panels for easier maintenance and changing around in an emergency before
very good
program?
question. In fact, the 8x8 the SAP is called LRU, line replaceable unit. And so you can swap one of them, take them out, and put the other one like that. It's all possible. And so we monitor temperature, we got all the noise figure, all the things for each of those elements in the whole system. We have whole temperature mapping because when you put the system on airplane, you can go to cooling and heating with a lot of things. I didn't show a lot of airplane-specific things. That is not a lot more other things, cooling and heat system. All the cats are recorded so that if there are problems with that, we can replace that one sub-panel taken out. In terms of if it becomes really big deal, then we got to, the reason why 4 are identical so that we can swap them if necessary, but you don't have to. At the same time, you can think about we don't see that far in the top panel. We don't see like 100 kilometer, gone about 15, 20 kilometer. The bottom, about 10 kilometer. We can scale them much smaller, could be done. But problem with that is beam will become very large because smaller aperture, since you're going to be poor. And so having this system are 4 identicals better because NRE cost is very large. Because you want to do it NRE cost, you can redesign the whole system, it takes time. Could be done in maybe in other systems, but for now, we stick with that 4 identical systems, see whether that's useful for us to, in a long-term maintenance. Like you said, how do you characterize system? Everything is same, then easier to do it, one after other, but if it's different, it's going to be a little bit more complicated. But as we go along, we learn about it.
Oh, we have a question from Bill.
So when this thing's not flying, is there thoughts about operating it from the
Pardon?
ground? When it's not flying, is there thoughts about operating it from the ground?
At this point, you haven't proposed that plan yet. That is something in the future. You can put all these 4 together, right? You can make it like a small, fine beam like that. We can make it. But this is, because at this point, you haven't got the funding for the APAR itself, and so you got to wait. If you make that one right, you got to demonstrate that, then there are opportunities. We can look into those possibilities. It's possible, yes, a C-band, phase data system. Yes, it's a good concept. We can do that. That way we have, when it's not deployed in C-130, we can deploy it on the ground, things like that. It's possible. That's why the system has a lot more potential to do like that, what I'm talking about. Like you have this, what you call the modular wind profiler, right? We have 3 or 5 or 9, you can put it how you want, like the same concept here. You can go, farther out or far less, depending upon PI's needs. Yeah, John?
Do you want to comment on what are the plans for going with either simultaneous or fast alternating transmit?
Or the transmit, okay. The polarimetric question, what John is asking. At this point, to reduce the cost or the complexity, both are important. We have just one channel. And so what we do is we transmit H, receive H, horizontal polarization. Transmit CV, the ATAR, alternate transmit, alternate receive. That's all we have. Now, even that, there is a wrinkle in that one. Radar has a lot of switches. Each switch costs you losses. You put a switch in a receiver or a transmitter, you got about 1.2 dB, 2 dB losses we get across. How do you eliminate that loss? Our aerospace company partner suggested, well, we can do that. We transmit 2 slant polarization to make it H and V like that. There's a newer concept how they're doing it. They have done for defense technology for this kind of stuff, and that's why I'm going to do it. It will be like we transmit like this, you get a V, it comes like they get an H like that. And the 2 cross poles could be done to avoid the switch. And so, okay, come with the question, it'll be alternate transmit, alternate receive. That's a single channel. We don't have a 2-channel receiver. 2-channel means you double that receiver. They're going to be expensive at this point. And so we try to make it as simple as possible. When polarimetric measurements, I didn't go into a little bit in depth. There are many things I can say about polarization technique. If you go away from the bore side, there'll be cross-coupling. How do you avoid that? And so we try to make it only scan a little bit from the bore side, not all the way here. People have shown we could be compensated, but that comes later. We don't want to do it in the beginning, burn ourselves, that we have to be careful what we can deliver to the community. And so we have been very conservative what we put together in the proposal. And so we will know in a month or so about MSRI decision for NSF. And there is a good future, and people have worked on this for many years. And so the people are highly talented here. They can deliver the system. Yeah.
Well, we have another question from the back.
Are you using the digital twin to simulate faults and failure recovery and detection? Monitor, like how to monitor that much equipment?
Adam, do you want to answer that?
We're sort of adding things to the simulator as we add them to the software. So once the software has that kind of capability, then if we want to go and test that, then we can add that sort of thing to the simulator. It's sort of designed with that type of thing in mind.
We have another question.
On the left and right panels of the airplane, they seem to be symmetrically placed, so they'd kind of be looking left and right sides. On the top and bottom, the top seems to be looking up and the back is on the loading dock. Is that backwards angle a problem or
Yeah.
a benefit?
Yeah, there are some, you are right. There are some weight considerations in this one, the cargo, how much can hold, few things like that. A lot of studies went on. And because of that, we have some issues with that. And so you have to scan, if you want to get scanning, it's placing like that back panel, it has to scan really upward like this to get a surveillance scan. Because surveillance scan is important. When you're flying into a tropical cyclone, you need to know, situation where you are. If you're a squall line, we can stay away from that. We can scan it like that. If you're flying into a huge, under our 200 kilometer size hurricane here, then you got to be careful. Where are you? That's why that top panel and the bottom panel and the side panel, nose radar, they're all important to get a surveillance scan. Then the PIs and pilot have the confidence how to go and get measurements done. It's it's exciting technology to look at it. But engineering challenges that could be solved. Like many radars, what we developed here, like a S-pole radar. We had before they get a CP2 radar. It's a Doppler radar. It took a long time to get to where we are today. It took more than, I would say, more than about 8 to 10 years to make polarimetric measurements as accurate as do it today. The first days when you did that, the accuracy of half a dB. Today we can look for 2/10 of a point. John can say that, but 2/10 of a dB we can do it with all the things. In the beginning, it won't work in winter time. It gives a lot of noise, the ZDR measurement, because the switch is not good. The Raytheon switch, what we had, the ferrite switch. Now it's much different. We have a MIT switch, so many other things we have it. And there are things have changed, and this will evolve as we move along. But this is just a first cut at it, what we are doing it. But it gives that a leap in technology, what we haven't done it. That is what we are looking forward to it.
Well, if we have no further questions, we are past the seminar hour. That was very interesting, and we look forward to seeing APAR as it develops and goes into the future. Let's thank our speaker.
Thanks for the attendance and really enjoyed presenting it. Really, I was saying, Jackie, I prepared it just for my own sake so that I can refresh myself what the APAR is. Thank you.